These two examples that we'll look at now have to do with critical numbers of a function. And recall that critical numbers are points at which the derivative of the function is either 0 or the derivative of the function does not exist. And the first one is fairly straightforward as a polynomial function, and the second one's a little bit more difficult as a trig function. Trig functions being cyclic, you have to be very careful as far as how you look at uh, how the answer is laid out. And we'll talk about that when we get there. First things first. Let's talk about, or let's find rather, the derivative of this function. Now this is a polynomial function. It is differentiable everywhere. And so we don't really have to worry about the second half of the critical number, which is where it's not differentiable. So let's take the derivative of this, and I'm going to use, rather than expanding, I'm going to use the product rule. So we take the derivative of the first, which is 2x times the second, plus derivative of the second times the first. Okay, and so we have the derivative of the function is 2x squared plus x squared is 3x squared minus 6x. When we set that to 0, then we can factor out a 3x, and this gives us x minus 2. This gives us either x is equal to 0 or x is equal to 2. Those are the two values that make that 0. Okay, so that means that we have critical points at, that's what I want to do. X is equal to 0 or 2. Okay. All right, so moving on. There are lots of ways that you can write this down, but this is just a matter of conveying it. So we have critical points x equals 0 and 2. You can also write the points if you wish to go back and find the y values for those 2 points in the original function. All right, in the second part here, we have this trigonomic function. And so we want to take a look at what its derivative is. Now this is going to utilize our chain rule. So we have the derivative of sine squared is 2 sine x times the derivative of what's inside. Derivative of what's inside is the derivative of sine, which is cosine. Okay, so it's the derivative of the outside times the derivative of the inside. Plus the derivative of cosine is negative sine. And if we set that equal to 0, we have now here, this part here is actually sine 2x. It's a double angle identity, so you have to be careful on these. That will help a lot. So here we have the sine of 2x minus the sine of x. And so if we solve, then we have sine of x is equal to the sine of 2x. I cannot stress enough, you have to be very, very cautious here. Okay, the reason you have to be cautious is that sines and cosines are cyclical. And so you can do this in several ways. I'm going to do this with using the unit circle. So I'll draw my unit circle here. Analytically, this gets very, very hairy, so I choose to go back to the unit circle when I deal with trig. Now, then when the sine of x is equal to the sine of 2x, okay, well that happens at 0. Okay, when x is 0, sine is 0, that sort of thing. However, we are restricted. We can't choose 0. Okay, that's a restriction on our open interval here because we need open intervals. And so that happens again though at pi, and so pi is a good choice. Other choices that work, 60 and 120. So if you look at it, and this kind of comes from just the science part of it, this makes it easier to see. Okay, now on the bottom here, I have to explain that just a little bit. But on the top, this is 60 degrees. This is 120 degrees, and you'll notice the sine values are the same. They're both the square root of 3 over 2. Okay, so this is 1/2, and this is negative 1/2. this is negative 1/2 or positive 1/2, comma square root of 3 over 2. Okay, so when x is 60, then 2x is 120, and they share the same sign values. So right now, as we list them, we have pi, we have 60 and 120, and so we have a solution at pi over 3, which yields 2 pi over 3 for the other angle. Excuse me. So that satisfies it. At pi over 3, then we have one. We also have one down here at this point. This is 5 pi over 3. When we multiply that by 2, we get 10 pi over 3, okay, which is actually 2 pi, and then we have some left over. And so if we subtract off that 6 pi, this is 4 pi over 3 at this point right here. So we have 5 pi over 3, and its match is 4 pi over 3. All right, so these are the three inputs in that range that you can put in. Be very careful here that you don't put in this one here, okay? Because that's actually the answer for the other one. So you have to be kind of cautious there. Before I saved it, I realized, okay, so I say that, but maybe I better explain that a little bit more. If you notice, with the tops here, the sign on the sign. So you're dealing with positive values in the y here. You're dealing with negative values here. Okay, so doubling 120, you might think, oh, why isn't 2 over 3 or 2 pi over 3 1? Because if you double it, you get 4 pi over 3. Yes, you do. But in that case, this is square root of 3 over 2. You're talking about talking about 2 pi over 3. This is the negative of it. And it doesn't work that way for sines. Sine is an odd function. And so if you take the negative of the input, you get the negative of the output. So that's why you can't just call it all of them. It's actually just these three that happen to have semi-mirror images about the y-axis. Okay? And that's another way to look at it as transformative. If you reflect it about the y-axis, then you'll end up with the same value. And so that's kind of nice that way.